Welcome. This video will primarily focus on digital electronics, but it's a part of a series that will explain how operating system works and computer architecture. I will only explain things that are necessary so you can understand how it all works. I won't go into too much details for that are unnecessary. So if you are watching this in hopes that you will learn things that your teacher or professor expects you, and by that I mean unnecessary stuff that goes in too much detail, that are completely unnecessary, you will have to go and find another video or research it yourself. Now let's begin. Now, there are several types of code for CPU, for PC, for computers. Today every computer is binary, but in the beginning there were PCs that used other types of code and computers that used other types of code. Now, all those types of code had their, advantages and disadvantages, and in the end binary is the only one that was good enough, or at least simple enough to use. There's not much to be said here, so let's move on. To code our human language into binary so the computer can understand it, Americans created ASCII. Now, the problem with ASCII is it only converts English signs, and when computers began to be widespread through the world, a new code was needed because, for example, Chinese or Russian or even French, they all have either a little bit different signs or completely different signs, like, you know, Russian. So Unicode was created. Unicode encodes every sign into binary. Again, there's nothing much to be said here. There were other types of code systems algorithms or systems that can code our human language into binary for different types of language, but again, they were all for that specific country, for that specific language, but as Unicode won because it could, okay, right. Let's move on. Now, how to code in binary. Here you can see numbers being coded in binary. As you see, there's a repeating pattern that is easy to understand. If you need some time to figure out the pattern, just pause the video. I won't tell you how it works. It's simple. Figure it out on your own. It's really not that hard. To the right, you can see two binary numbers being added together. That's 10 and 13. That equals 23. The first number all the way on top is 10. The middle one is 13, and all the way on the bottom is the result 23. Now, when 1 plus 1 happens, it equals a 0, and a 1 is being carried to the left. Now, in this case, we have nothing on the left once 1 plus 1 happens, so we just write it down next to that 0. Quite simple. But it changes when it gets to something like 1 plus 1. Then 1 plus 1 will equal 0, but you have to carry that 1 from before. That 0 will now equal 1, and you have a new 1 to carry from the 1 plus 1. Again, there's nothing much to be said here. You can try, I hope you will try to reverse engineer subtraction from this, because I won't tell you how to do this. It's better for you because it's easier to learn something when you figure it out on your own than when you actually hear from somebody explaining it to you. At least for most of the people it's like that. Now, let's move on. The fundamental components of every computer. Now you think probably I'm talking about RAM or motherboard. No, I'm not talking about any of this stuff. I'm talking about the smallest stuff. For example, in CPU, there's memory cache, control unit, ALU or arithmetic logic unit. Now, ALU is made of logic gates. Now you must be wondering, what are logic gates? They are the fundamental components of a computer. They are literally that. I don't know how else to explain this to you. Now, here on the screen you can see a 4-bit version of ALU, which is quite old. Well, let's move on from that. I need to explain how many are there and what are they now. There are 7 of them. Here are the names. They are quite simple to learn. First one, just not or inverter. As you can see, it just inverts. If 0 comes in, 1 comes out. If 1 goes in, 0 comes out. You can draw it in 2 different ways, so you know. Now AND, for AND to output be 1, you just have all inputs have to be 1. So, and by the way, unlike NOT, every other logic gate can have multiple inputs, just so you know. So, for AND to have an output of 1, every input has to be 1. If one input is 0, the output is automatically 0. Now, or only one input has to be 1 for the output to be 1, or all can be 1 for the output to be 1. NAND is reverse from AND. Either all inputs have to be 0, or only one input has to be 1 for the output to be 1. But if all inputs are 1, then the output is 0, because NAND is an also inverter. It gives the same results as AND, but at the end, before they go out, it inverts them. It's quite simple. Like imagine, after the AND, you put an inverter or not. This is basically the same thing, but they're merged together into one thing, and they're called NAND. It's called NAND. Now, NOR, again, also can invert, like OR. It's like OR, but it inverts. Here, all inputs have to be 0 for the output to be 1, where in OR, only one input has to be 1 for the output to be 1. Here, all inputs have to be 0 for the output to be 1. XOR is a little bit more complex. Here, only one input has to be 1 for the output to be 1. But if both inputs are 1 or 0, the output is 0 automatically. And XNOR, inputs have to all be 0 or 1 for the output to be 1. Any other combination will result in 0. Now, if this makes your head spin, don't worry. When you actually deal with schematics like this, you won't really use ones and zeros, right? You'll probably use algebra, and I mean regular algebra, I mean Poole's algebra, and you'll probably be using minimization at some point. Now we will get to this. Here's Poole's algebra. It looks scary, but trust me, it isn't. I'll explain how it works. Now here I will explain how this works. So basically, here P gets inverted with this. So P gets inverted here, and B and C get added here. So B already being inverted, it's added here with C. This is basically a plus here. Now as A goes, A splits, and it goes here. This is a multiplier, so this multiplies. So here we get A times B inverted plus C. Quite simple. Here D gets inverted. Well, never mind. D gets inverted here, and as it gets in here, where it gets multiplied, it gets multiplied with A, so it's A times D inverted. And now all of that goes here, gets added, and this results in this. that. Not that hard. This is a simple task because it just represents plus and multiplication. Now you can go much farther with the other ones, but again the principle is the same. This was just a simple example to be said. That's it. Now here you can see minimization. So basically minimization is when you have a big circuit and you need to minimize it somehow. So instead of just sitting around trying to figure out how to rearrange it to get the same result but with less logical gates, you can turn it into a function, minimize the function, and then from the new function create new set of logical gates that will do the same thing like the first one did but with less of them. So basically we convert the bigger one into the left formula, the one at the top. It's x inverted y inverted z plus x inverted y z plus x y inverted. So we take the first two, the first sets x inverted and the next one x inverted are both inverted. We can copy that. Y inverted and y are not inverted. We do not copy them, they cancel each other out. Z and z are both not inverted, they are both the same. We copy them and then we just copy plus x y inverted. Now we have a new function that's minimized, and from that function we can recreate a new set of drawings for the logical gates. Now here's a much complex version of it, as you can see, but it's the same principle. It's the same. You keep minimizing as much as you can till you get to the end, till you can not minimize anything at all. You just look what can cancel each other out. For example, here we have a b c inverted d inverted plus a b c inverted d. We can already see that everything is the same except d. One d is inverted, the other one is not. They can cancel each other out. Everything is copied down, and you keep going like that until everything you can is cancelled out. That's about it. Thank you for watching. I hope you had fun. And I hope you actually, understand what I showed you today. And I'm sorry for the bad sound. I have a bad microphone and this is my first time doing something like this. Thank you and goodbye.